time to begin. Our today's speaker is Dr. Boris Doubrov from Minsk, and as you see, he will speak about geometry of Cauchy Riemann manifolds via finite-type systems of PDEs. Boya, you are welcome. Please begin.
Hello, everybody. It's always a pleasure to take part in this seminar. And the talk today is on the edge of two seemingly completely unrelated subjects. One of them is the geometry, it's a complex analysis object. It's an object which is called CR manifolds. And another one is directly related to the topic of the seminar. This is geometry of systems of PDEs, though it's a special type of systems. I will explain soon what they are and what is the relation here. So a very quick, for those who hasn't seen before what is a CR manifold, a very brief introduction. So whenever we have a real submanifold in CN, they always inherit a special geometric structure known as CR manifold or Cauchy-Riemann manifold. And we normally view them under holomorphic transformations of CN. So we'll see that complexifying CR manifolds leads to another geometry, which is geometry of pseudo-product structures. This is maybe a bit confusing terminology, but it comes back to the works of Japanese mathematician Tanaka. And it turns out that many local properties, well, whenever we do complexification, of course, we lose something, but many local properties especially remain essentially the same. And in particular, we would be able to use the geometry of PDEs here because pseudo-product structures is more or less the same as systems of finite-type PDEs. And what is a system of finite-type PDE is just a system of PDEs that has finite-dimensional solution space. So the solution spaces of our we will have overdetermined systems of PDEs, and their solutions will be parameterized by a finite number of parameters. So these are not really very typical PDEs. They behave more like ordinary differential equations, in fact. So after some prolongations, they would be reduced to Frobenius system. Well, I mainly try to show some examples here. I'll mention some theorems. So this has been in work for the last maybe almost 10 years. There were some results on the way. There are still open questions. And well, the idea of this talk is to introduce you to the subject and via many examples. Well, a very naive and very typical introduction, very typical case is when we have a codimension one real submanifold in Cn+1. So it's a real 2n+1 dimensional hypersurface. We introduce so-called complex tangent space. It's just a tangent space to M intersected with its complex conjugate. So tangent space to M will be a codimension one subspace in Cn+1 viewed as a 2n+2 dimensional real manifold. So conjugate is also a codimension one intersection will be of codimension 2 in Cn+1, real codimension 2 in Cn+1 viewed as 2n+2 dimensional manifold, or we can always restrict it to M itself, and it will have just a real codimension one in M itself. And this complex tangent carries naturally complex structure. Even if M itself is real, there will be a complex, well, multiplication by imaginary I seen as just a complex structure of this distribution. Well, vector distribution D itself is codimension 1, and the most typical case when it's just a context structure. So we call M Levino degenerate. I'll soon define what is Levy form. So we call it Levino degenerate if D is a context structure. So a most typical intrinsically defined CR geometry is a contact manifold with a complex structure on this contact distribution that agrees with the Lie bracket. For those who like coordinates, so in coordinates, suppose we have complex coordinates normally defined as denoted as W, Z1, etc., Zn and Cn plus 1. Then up to holomorphic transformations, we can write locally the equation of M in this simple form. So imaginary part of W is just a quadratic form and Z1, etc., up to Zk, plus some higher order terms. And we say that M is not degenerate, and this is the same as saying that D is contact, if and only if this quadratic form has the right number of variables. So it's all variables present here. So N is equal to K. And well, actually, this quadratic form is what's naively called a Levy form. So Levy non-degeneracy means that this form in N variables has to be non-degenerate. In particular, the nicest hypersurface in this geometry is this one. And that is what appears as an analog of like, I don't know, straight line in projective geometry, for example. Like here, we speak about this as the nicest geometric object. So what is the pseudo-product structures? So now being a bit more formal, CR manifold is any smooth manifold equipped with a vector distribution D and a complex structure in it compatible with the Levy form. So by Levy form, we just mean a bracket of vector fields inside D modulo D itself. So it's lambda squared D going to D squared by D. And compatibility is essentially defined here on this line. So this complex structure has to be symmetric with respect to the Levy form. We normally impose, all our structures will come from submanifolds in Cn. In this case, these structures are integrable. And this is similar to the integrability of complex structures on manifolds, not just on a vector distribution there. This just means that if you consider eigenspaces for this operator J on complexified D, because well, on D itself, it's a complex structure, it will have no eigenvalues. So we complexify D, we look at the eigenspaces with respect to I and minus I, and we assume that these two are completely integrable. This is integrability condition. And in this case, actually, any such manifold abstract, well, we need to assume not just smoothness, but analyticity here, but any analytic manifold with integrable G can be embedded into Cn to become exactly a real hypersurface, a real submanifold such that this structure is induced from Cn. Well, this decomposition of complexified D into two subspaces, which form completely integrable distributions, motivates us to define a more general structure. And this is what was introduced by Tanaka back maybe in 1970. So a pseudo-product structure on a smooth complex analytic manifold is bracket generating distribution D. So bracket generating means that when we take brackets inside D, it after some iterations, it will span on OTM. And the decomposition of D into the sum of two completely integrable distributions. So if D is compact, sometimes such structures are called Legendrian or integrable Lagrangian. There is a confusion here whether they're Legendrian structures because E and F become Lagrangian subspaces inside D. But anyway, so this is one of the most studied cases maybe, but the definition has makes sense in full generality here. Well, how it's now related to differential equations. As I mentioned before, systems of differential equations are said to be of finite type if solution spaces are parameterized by a finite number of parameters, which are constants of integration. Well, scalar ODEs is a very typical example, but of course, overdetermined PDEs may have such form as well. And well, we may have a system like this where you have certain number of unknown functions, certain number of independent variables, and PDEs can be of arbitrary order here and actually mixed order. So this is a completely general system of PDEs with the only requirement that, well, it's compatible and it has finite dimensional solution space. Sometimes it's not readily seen what are the compatibility conditions and what is the dimensional solution space. Like, for example, if you start with a system like this, it's not immediately clear that you need to differentiate it 2 times till it becomes till you get all 4th order derivatives expressed to lower order derivatives, so it becomes finite type clearly. And of course, there are quite complicated compatibility conditions on functions of G. So that for any initial conditions, we get a unique submanifold, a unique solution. Under a very mild regularity conditions, actually any such system of finite type PDEs is encoded or is equivalent to a pseudo product structure or a double fibration. So where does it come from? Suppose we have such finite type system, it has a solution space, and it is viewed as suppose we have n independent variables and m dependent variables, then any solution can be viewed geometrically just as an n-dimensional submanifold is in n plus m dimensional smooth manifold M, where ui, xj are local coordinates. If you have solution space that is finite dimensional family of such submanifolds, we may have incidence submanifolds, so we can take direct product of our manifold M and is a manifold or constants of integrations that parameterize solutions. And inside we have an incidence submanifold, which says for each constants of integration, which submanifold we get as a solution, which points belong to the solution. And locally, the general solution of such system can be written as this very general system. So we have our independent and dependent and independent variables. We have constants of integration, and then we have some number of equations defining this incidence submanifold. But that's exactly how you can also define pseudo product structures. Well, that's what I mentioned. So it's actually vice versa. Any incidence submanifold can be also viewed as a finite dimensional solution space, and therefore, if you differentiate such system a few times and exclude constants of integration, you'll end up with defining system of PDEs. Well, one nice thing about looking at these equations is that there's certain duality here. We can swap manifolds M and N here, so they are fully symmetric in this incidence relation. And this is a kind of duality that is present in some and plays important role in some examples. So how this can be related to the geometry CR manifolds? Suppose we have a real analytic submanifold in Cn plus M of real codimension M, and shared dimension. By shared dimension, we mean exactly the complex dimension of our complex tangent space. So classically, we can write such submanifold in this form, where Z is from Cn, W is from Cn, and so this is actually a system of equations and equations here. And of course, since this has to define the real submanifold, there should be some compatibility condition here. So what do we do if you want to complexify this? We just introduce new complex variables, A and B from also Cn and Cn. And we consider a new complex submanifold. So M was a real submanifold. Now we have a complex submanifold in double dimension. And the defining equation is the same, where we just replace Z bar by A and W bar by B. So complexification is looking at the same defining equations, but unlocking Z bar and W bar from Z and W. So we now really treat Z bar and W bar as independent, as new variables, complex ones. So it's a very simple trick invented back by maybe, I don't know, people from complex analysis may know it better. I know it from Segre varieties. But this is how you can turn any real analytic submanifold in Cn plus M, so essentially any integrable CR manifold, into this system. And we've seen before that if we treat A and B as constants of integration, we can view this as solution space of a finite type system of PDEs. So there is a direct way to go from CR manifold to a complex system of PDEs of finite type. Yeah, so that's exactly what I said. Let's look at a very simple example. Well, maybe second simplest. The first one would be to look at our model, flat model. But let's, for example, look at a very classical Winkelmann surface. So this is the equation. It looks quite complicated here. Well, to me at least, it's certainly, so on the left-hand side, we have something of second order. On the right-hand side, we have something of fourth order. But then if you complexify things, it turns out into just a single equation. So we had single equation, defining equation here. So it is also a single defining equation now here. So you can maybe recognize what has happened. For example, here, Z1, module of Z1 to the degree 4 turned out into A1 Z1 squared. And we get 2 because when we interpret the imaginary part of the thing, we have to subtract and divide by 2. So we move 2 to the right-hand side. So now we have to think about W as a function of Z1 and Z2, and A1, A2, and B as constants of integration. So we start differentiating the things, excluding them, and we end up with this system of PDEs where W11 is the second derivative of W with respect to Z1, and so on. So this is a standard notation we use for PDEs. This Winkelmann surface corresponds to this finite type system of PDEs. And that's certainly a question of preference or taste, but those people who deal with complex analysis maybe would prefer this equation. those people who deal with geometry of PDEs would probably like this system, well, would understand such system of PDEs better. Well, now it's time to speak a little bit about different notions of non-degeneracy, because we'll need some. We don't want to discuss only non-degenerate cases. We also want to cover degenerate cases here. So again, there is a certain link between the language of complex analysis and the language of well, vector distributions and also differential equations. So CR manifold is called minimal if D is bracket generating at a generic point. And and then, well, similarly, if you have a pseudo product structure, we by definition assumes that D is bracket generating, and one of the weak regularity assumptions is that if you start taking brackets of D, it generates so-called weak derived flag of D. So all elements of this flag will also be vector distributions. And after some number of iterations by regularity, we have to reach all tangent space. And then we already mentioned that we have a Levy non-degeneracy. So this is a Levy form that can be defined just as a bracket vector fields inside D modulo D itself. So we say that CR manifold is called Levy non-degenerate if this thing is not degenerate. Similarly, in pseudo product structures, actually, because E and F are both completely integrable, then Levy bracket can be reduced to just a bilinear form on E and F with values in D squared by D. So we say that our pseudo product structure is not degenerate if again Levy form is not degenerate. However, sometimes we need degenerate Levy forms, and then we have different levels of degeneracy. So suppose now we have a degenerate Levy form. This means it may have left kernel, it may have right kernel, it's just bilinear form. But suppose it has a kernel, then we define like E0, for example. Suppose it has left kernels, then we define E-1 as E, E0 is the kernel of this Levy form. And then we iterate, for example, E1 is those vector fields from E0 which bracketed with F stay inside E0. And we get a sequence of decreasing subspaces inside E, and similarly, sequence of decreasing subspaces inside F. They can be viewed as kernels of first order, second order, third order, and so on. They also have a natural interpretation if we, in terms of Taylor series or of the equation defining our CR manifolds, but this is a purely geometric definition. And for example, E0 plus F0 is exactly the characteristic distribution of D itself. And often in differential geometry, especially, we assume that whenever we have characteristic direction, we quotient by it and consider what comes out of after quotienting. But here we want to have complete filtration inside E and F available to us, and we say that the KL non-degenerate if if the filtration inside E after K steps becomes 0, and the same for F. So inside F we get kernels, but of higher order, and eventually they terminate at 0. And this is known as, in the case of CR manifolds, our E and F can be viewed as just eigenspaces of complex structure with eigenvalues I and minus I. So we have absolutely similar definitions. And this filtration is known as Freeman filtration or Freeman sequence. Of course, because in this case we have this, well, the store eigenspaces are complex conjugate, they will have the same lengths. But if it's just an arbitrary pseudo product structure, it's not necessary. And I speak so carefully about this definition because it will show up soon in the language of PDEs as well. But very quickly, this is well, a little bit. It's old stuff that was completed maybe 5-6 years ago, and this is the case of non-degenerate hypersurfaces. Means it's just a hypersurface in a C, well, n+1 maybe, or n, whatever you prefer, and it's Levin not degenerate. Then it turns out that the corresponding systems of PDEs are always complete systems of second-order PDEs. So these are complete systems of second-order PDEs, quite well-known subject. And in terms of pseudo-product structures, we have a natural interpretation where E is just, we look at this in jet coordinates. So we look at this, the interpretation of this second-order system of PDE on first jets. And on first jets, we have direction that is tangential to first jets of solutions. And the second one is a projection from first jets to zero jets. And they form these two completely integrable subspaces inside contact distribution on first jets. And compatibility conditions are actually the same as, so compatibility conditions of the system, if you assume compatibility conditions, are exactly the same as complete integrability of this vector distribution. The geometry of such things is very well known. It's actually so-called parabolic geometry, and we have a natural Cartan connection, and we can solve the equivalence problem for such systems. For example, we compute a curvature of such geometry, and it turns out to be exactly like that. And it gives us explicit conditions when such system is equivalent to the trivial one, where all right-hand side vanishes. And of course, the trivial one corresponds to this flat CR model we've seen in the first slide. So we have a very explicit way to understand. So if you start with any CR hypersurface, we have a very constructive way to understand whether it is locally equivalent to the flat one or not. We just need to turn this into the system of second-order PDEs after complexification and compute this tensor. It's state-free part of this tensor. So, well, it's a straightforward computation, even hand computation. Most studied case maybe is when we speak about three-dimensional real hypersurfaces in C2, but that's a very classical story back to Lee Cartan in 1930s, and maybe even 20s.
Sorry, Borya, may I ask a question?
Yeah. Sure.
Zhenya Ferapondov.
So
compatibility conditions for your system should be first-order PDEs in this FIG, right? You just compute third-order derivatives, and compatibility are first-order relations. But why then curvature is second-order expression? I can't understand this.
Well, curvature doesn't measure compatibility. So compatibility is the condition that we need in the setup of our geometry. So Fij indeed satisfy first-order PDEs to guarantee that this distribution E, well, the system is compatible and this distribution E is completely integrable. If these compatibility conditions are satisfied, we may still have different non-equivalent systems. Some of them will be equivalent to a trivial one, where right-hand side is zero. Sometimes it will not be equivalent to the trivial one.
Okay, I see.
So this tensor measures exactly the case when, like, flatness condition. So flatness is not the same as compatibility.
Okay, thank you.
So essentially, the tensor the vanishing of this tensor says us when the symmetry algebra, for example, for the system becomes gets maximal dimension. Okay, so again, a very well, standard case which was studied in some earlier works is exactly when we have two independent variables and one dependent, then we have this system, three functions, and then this harmonic part, or what this curvature can be interpreted as nicely as this tensor. So it's a binary quartic, where actually, yeah, P, Q are, well, first derivatives of U by Z1 and Z2. And R and S are just artificial coordinates introduced for algebraic reasons. So we have a very explicit binary quartic, and these are exactly second-order derivatives that come from this state-free tensor. And the analysis of such systems, equivalence of such systems, is actually the first step is to understand what is the root type of this quartic. And as in case of Petrov classification, or some other works where we have quartics, we have types of the geometry based on the multiplicities of rows. I just introduced this notation because I'll occasionally use it. Now, some time ago, we did a complete classification or classification of all such systems which are compatible and which have sufficiently large symmetry. Namely, which have at least 6-dimensional symmetry, so 5-dimensional plus 1. 5-dimensional to be transitive on the first jet, and 1 with stabilizer. And that was a massive work, and I just introduced some notation. Maybe it's not that important. I just wanted to give you an idea that it is possible to have a very explicit classification in such case. So any complete system of second-order PDEs with at least 6-dimensional symmetry algebra transitive on this space is contact equivalent to one of these families. So there are very explicit expressions for U11, U12, U22, and there are some notation here. So first letter is the type, second number is the dimension of the symmetry, and is D means self-dual or not, which means that if you swap E and F, either the system will become equivalent to the original one or not. Certainly one of the applications of such classification was to extend it to the classification of CR hypersurfaces in C3, or real hypersurfaces in C3, which are Levinian degenerate, which have sufficiently large symmetry. And it turned out that, well, that was possible, and we managed to complete this classification starting from some earlier work. And I see Professor Loboda here on the call, so he's certainly one of the great contributors in this area. So I need also this terminology here because these are the examples I'll show you very soon. So this is called tubular CR hypersurfaces. Very briefly, a hypersurface in CN is called tubular if it is defined just as a single equation only on real parts, or maybe on imaginary parts. So, but well, let's assume on real parts of variables. So, and they're characterized as having an abelian symmetry algebra spanned by translations along imaginary part. It turns out that if you complexify them, we get a very nice family of complex hypersurfaces in complex affine space. Namely, we just pick up an arbitrary hypersurface in AN and act on it by all parallel transports. Well, we assume that S is not, well, we have to assume that S itself is not a cylinder, so it's not stable with respect to any of the translations. Then we always have an n-dimensional family of hypersurfaces NAN, and it is defined by some system of PDEs. So if we write this system explicitly, we can actually characterize what kind of systems we get. These are exactly systems of PDEs which possess all parallel transports of symmetry. So it's actually a nice relation between affine geometry and second-order systems of PDEs, as well as so-called tubular hypersurfaces in CN. And for example, some geometric properties are not nicely translated. Rank of Levi kernel is exactly the same as the rank of second fundamental form of S. So we know that what we get will be Levi non-degenerate if and only if we start not just from non-cylindrical surface, but we need to additionally require that S has a non-degenerate second fundamental form. Some examples of hypersurfaces with large symmetries that came out of this classification from this classification. I don't want to give the complete list; it's quite complicated, but there are certainly tubular hypersurfaces in CN that come from homogeneous affine hypersurfaces. These are the equations. Well, there are very nice hyperspheres with semi-simple symmetry. Their equations can be written very explicitly like this. There are very strange ones which have very special kind of equations, and I'll give you some more precise examples here. So these are examples of equations in CC where we have X, Z, and W as coordinates. So in particular, alpha equal to 2 in the first example does correspond to Winkelmann hypersurface, and for arbitrary alphas we get more examples. And this leads to so-called homogeneous unbounded domains in C3. And again, I don't, in this talk in general, I don't speak much about all the references. There's a long list of references, which I probably will provide. I didn't include this into my slides here, but when I distribute the slides, I will add an extra information. But that's a huge list of references going back to classical works like Elie Cartan, but also to the recent works of Professor Labada and his collaborators, and also some other groups of people who were actively investigating such questions. Well, maybe out of curiosity, there is a very interesting result that the only non-tubular hypersurface in C3 with simply transitive symmetry. So before I was speaking about hypersurfaces and equations with at least 6-dimensional symmetry. These are the ones that have exactly 5-dimensional symmetry, and they are either tubular, so they come from affine surfaces in A3, or there's exactly one example, again discovered in the work of Labada. Here's an explicit expression. Symmetry algebra is isomorphic to semi-direct product of SL2C. Semi times, well, should be C2. Oh, I don't know why it's RC here. So this is the symmetry here, and curvature has type 1. All roots are simple. A very funny way to understand the geometry of the thing via equiaffine geometry. So equiaffine geometry, if you take 2 points on equiaffine plane and then take an x, so xy is a coordinate of 1 point, AB is a coordinate of another point. Then we have a slope of a line through point xy and the slope of a line through point AB, so essentially coordinates of the first jet. Then they define as a triangle, and the area of triangle is, of course, equiaffine invariant. So if you make it, if you assume it's constant, you can normalize it to any constant we wish, for example, 1. We get a quite complicated equation involving x, y, u, and a, b, c. So we exclude a, b, and c from this expression, and we get a huge PD. And actually, the PD is like that. So we have to write 3 invariants of this Lie algebra I've seen before. I showed before. So these are differential invariants of the action of Lie algebra G acting on second jet. So it's 5-dimensional, jet is 8-dimensional, so it has 3 invariants. And then we have an arbitrary system of PDEs like that, where alpha 1, alpha 2, this is absolute invariant, so I can just assume that they are constant. And this unique hypersurface corresponds to the system of PDEs where the constants alpha 1, alpha 2, and alpha 3 are very strange. Well, they can be a little bit simplified, but not much because they have to satisfy an algebraic equation. And in general, this system is not compatible, so it will be compatible only under the conditions that alpha 1, alpha 2, and alpha 3 satisfy some algebraic conditions again. But this one does satisfy this algebraic conditions, so it's not straightforward at all to see that such system is compatible, actually. Not to say that it has the solution space. Well, so I switch now to the last part of my talk, and these are degenerate examples. Now, I mentioned before that, well, essentially, we can think about just finite dimensional families of submanifolds somewhere. So in some finite dimensional manifolds. So here, let's look at the 3-dimensional family of hypersurfaces in R3. So we have 3-dimensional family of hypersurfaces. And how do we understand what kind of PDEs we get if you want to exclude this constants A, B, and C? So of course we assume no zero-order equations. So this means that through each point in R3, X, Y, and U, we have at least one such hypersurface. Now we look at first jets. So essentially we look at all tangent planes. So for each A, B, and C, for each, if you fix A, B, and C, that's a single 2-dimensional surface in R3. So it has a 2-dimensional plane. So a family of all such planes can be seen as a family of points on first jets of maps from R2 to R. Now we have two cases. Either this family is generically open, so it does not satisfy any first-order PDE, or it satisfies. So if it does not satisfy any first-order PDEs, and we can leave them further to second-order jets, and we'll end up exactly at the non-degenerate case, which we discussed before. But we may occasionally have a first-order PDE at that step. So in the degenerate case, we may have a single PDE of first order, and we assume that we could write it like that, introducing some appropriate change, maybe coordinates X and Y. Then to have a 3-dimensional family, we actually need to add a third-order PDE to it, not the first, second order, because if you have UYY expressed through some lower-order derivatives, we would get only a 2-dimensional family of surfaces. And in order to get a 3-dimensional family, and well, the reason why I need 3, because I want to have 3 coordinates X, Y, and U, and 3 parameters of integration. So I want to have the same number of hypersurfaces as the dimension of my manifold, just in order to get most symmetric cases, or self-dual cases, maybe. So essentially, the degenerate cases in such simple situation would be encoded by this, well, maybe not that straightforward, well, not typical system of PDEs. Again, it should satisfy certain compatibility conditions, and we can introducing like jet coordinates P and Q here, so we can encode such system as 2 distributions. Again, one of them will be a distribution tangent to all solutions. And the second one is a projection to X, Y, U coordinates to 0 jet. And compatibility would mean that this distribution is completely integrable. Now we compute Levy form, and we get what we would expect. So we have Levy kernels of Levy forms. They are one-dimensional. So E and F are two-dimensional. Inside the E and F, we have one-dimensional kernels. And if we compute kernel of the next order, we see that E1 is 0 if and only if the function f in this equation has the non-zero second-order derivatives with respect to uy. So this is non-degenerate, real non-degenerate. Well, this is like weakest non-degeneracy assumption we have to assume in order to get something meaningful. So we have that in the end, the system of PDEs defines a 2-2 non-degenerate pseudo-product structure if and only if f is non-linear in UI. And very typically in such cases, when we understood what are our restrictions on the right-hand side to have something weakly non-degenerate maybe, we would like to understand what is the easiest system, and we write the system like that. So we assume that W1, so derivative of W by Z1 is indeed something non-linear, and the simplest non-linear function in W2 is of course square. And the second equation we keep trivial, and that's very easy to solve. We get very nice solution space, now parameterized by 3 constants of integration. I denoted them for symmetricity as A1, A2, and B. And the symmetry algebra is 10-dimensional, isomorphic to SP4, and that is the maximal possible dimension of a symmetry algebra for this two non-degenerate pseudo-product structure on a 5-dimensional manifold. And now we take a real slice, so essentially real form. We try to return from complexification to the real form, and we have this well-known cone equation. So this is a very typical equation in this area of CR manifolds, where that's maybe most well-known example of degenerate CR hypersurface. It's of course tubular, because equations involve only real part here, and it's just an affine cone in C3. So what happens if you repeat, if you write, so now I finished my talk by a series of some examples and then open questions. So consider now a possible generalization of this example to C4. So write it as another cone in C4. So what would be the system of PDEs that corresponds to this cone? So how to do that? Again, we have a very straightforward way to go from this system to a finite-dimensional space of potential solutions of subsystem PDEs. So it's 4 parameters here, imaginary parts of W, Z1, Z2, Z3. Well, this is the system of PDEs. So we again have one system of first order and 2 systems of second order now. So before we had one equation of third order, here we have 2 equations of second order. And again, it's maybe not straightforward to see that actually we need to prolong it a little bit further because, for example, W12 is not defined. So we need to differentiate it twice to end up with a closed form system. But again, the system is compatible. It has exactly 4-dimensional solution space. Actually, this is the solution space, and it corresponds to this nice degenerate CR manifold. So it has, it is again 2 non-degenerate, has 1-dimensional Levy kernel, and you can actually generalize this to any other example, just defining such cones and the corresponding equations. Well, we can generalize the example we had, like this one, in the other direction. So we introduce more coordinates. And now we have 3 first-order PDEs. So W3, W4, W5 are expressed as through first-order derivatives in quadratic way. And with respect to 1 and 2, we have all derivatives, all third-order derivatives equal to 0. And again, that's just a way to generalize such systems. And you end up with exactly 6-dimensional solution space and a very nice affine hypersurface, which if you write it explicitly, it will have, it is homogeneous of degree 3. And now it is a cone of degree 3. It is also 2 non-degenerate and has very large, well, 3-dimensional V kernel. So it's just how you can write very interesting, probably unknown. This is the first example of such hypersurfaces. Well, I do have the computation for the symmetry algebra. I don't remember it exactly. Yeah, so there are more people working in this direction, like Marini, Midori, and Nesinovich. And you can even go one step further, and you get this kind of, equations where you start seeing some kind of rational curves showing up here, because W3, W, etc., Wn are parameterized by powers of W2. W2 is is also first order derivative. So this all equations except for the first 2 lines are first orders, and we have 2 equations of second order, and then we have exactly 1 equation of nth order. And again, we have a very explicit solution, and or very real slice, we have a CR hypersurface. Again, it turned out that it was known before. I think it's the work of Labovsky from Beloshapka school, if I understand correctly. But so he was probably the first one to write explicitly this CR hypersurface, but I don't think he has ever tried to do it on the language of PDEs. So these are examples of maybe a bit strange, but to me very interesting systems of finite type PDEs, which of course can be deformed a little bit. So you can add arbitrary functions here with appropriate non-degeneracy conditions, and you would derive, assuming compatibility conditions, you would derive at very interesting CR hypersurfaces. So I stop here with the examples, and I finish with some open questions. So it's not completely clear now. So we have this filtration which defines you different levels of non-degeneracy for CR manifolds or pseudo-product structures. So it's not clear yet how dimensions and depths of this Freeman filtration can be described in terms of the corresponding systems of PDEs. For example, in this case, we know that this system below is a K non-degenerate example for any K greater or equal to 2. Well, actually, it's K is the same as N, probably. Yeah, it's here. Yeah. So it looks like the level of non-degeneracy does correspond to the maximal order of PDEs we have. So essentially, how to which jet we have to lift all our submanifolds in order to get a Frobenius system. But the dimensions are completely unclear. They probably correspond to the number of initial conditions at each of each order that we need to fix in order to get a unique solution. Then we have a very nice conjecture that is still open. So any finitely non-degenerate pseudo-product structure has a finite dimensional symmetry. It's been known in CR case, but the proof is far from being trivial, and I don't think, well, it uses, well, we tried to understand the proofs, but they lead to complicated complex analysis, I would say. So in particular, they clearly do not generalize to smooth pseudo-product structures. But it seems to be that there is a purely geometric way to prove such statement. So far, we haven't seen any single example of non-degenerate finitely non-degenerate pseudo-product structure with infinite symmetry. And of course, and in a more general question, how to solve equivalence problem for this kind of structures. For example, how to construct absolute parallelism of certain invariants, maybe Cartan connections if possible. That's also not known in general. And we really believe that the language of PDEs may help to solve these problems. For example, this conjecture translates immediately to the question, suppose we are given a finite type system of PDEs, is it true that its symmetry algebra is finite dimensional as well? And under some, well, mild, but still there would be some regularity conditions. So we can reformulate maybe in terms of PDEs, we have to, it would be more proper to say which non-degeneracy conditions we have to assume to guarantee that the symmetry algebra of such system is finite dimensional. I don't have any answer to this question yet, but as I say, so we think that this bridge between CR geometry and language of PDEs may help. Okay, so that's it. I stop here.
Okay, Boris, thanks a lot. Well, of course, it's quite interesting, and just remember that you're always welcome here. Questions, remark? Zhenya, no question, no remark. Okay, thanks a lot.
Not at this stage.
Yeah.
Yeah, I understand my talk is going into like a very special direction, and yep.
But quite interesting relations. Yeah, okay. So thank you for visiting the seminar, and we meet in a week again in Zoom.